So what we have here is two wave pulses that are travelling towards one another. So imagine perhaps, if you like, a spring, and the coils of the spring then and the medium transferring two wave pulses through this spring, both of which have got sort of a positive displacement here, and they're moving in opposite directions, they're moving towards each other. What will actually happen as those wave pulses cross is they will reinforce each other, and what we will arrive at here is a larger amplitude wave as they cross over and will reinforce each other. What we call constructive interference is taking place. Now this is in accordance with the principle of superposition, which is that when two waves of the same type cross, the displacement at any point will be equal to the vector sum of the displacements of the individual waves. So basically, as these two wave pulses cross over one another, their positive displacements will add together, gives a larger positive displacement. What about if we have the same medium? So again, it could be a spring, be a string or whatever. You're sending two wave pulses here through this in opposite directions, but one of them here has got a positive displacement and the other, if you like, has got a negative displacement. The displacements are in opposite directions. What will happen as those pulses cross over? Well, again, we can apply the principle of superposition. The displacement at any point as they cross will be the vector sum of the individual displacement. So when we add those together, they will cancel each other out. A process that we term destructive interference. Here, a process called constructive interference has occurred, and in this case on the right, we have a process that we term destructive interference when cancellation has occurred. So this is happening in accordance with the principle of superposition, which is that when two waves of the same type cross, the displacement at any point is equal to the vector sum of the displacements of the individual waves at that point. And that's what we can see here. So what we will do here now is to consider what happens if we have two waves of similar amplitude, same frequency, travelling in the opposite directions at the same speed. So the easiest way to produce this situation would be to have a wave and its reflection. So imagine perhaps taking a wave, reflecting it from a surface, so maybe a microwave reflecting it from a surface, and allowing the reflected and the incident waves to superpose. What would actually occur? Well, this is the situation we would have here. So let's say here we've got this wave, it's a transverse wave in this case, and you can see here these dotted lines represent a quarter of a wave period, a quarter of a wavelength basically here. So you can see two pairs of dotted lines is half a wavelength, and there we've got a full wavelength. Now, at this particular situation, situation 1 here, you can see that the waves will interfere destructively. Destructive interference will occur and the waves will cancel out, because if you like it, a wave crest here on this wave is matching up with a wave trough, so we've got a positive and a negative displacement adding together. They will cancel out. Later on here at this point in the wave, we've got a positive displacement on this wave but a negative displacement on this one. Again, they will cancel out again. Destructive interference will occur and we'll have complete cancellation. Now what we're going to do in situation 2, we're going to imagine a time a little bit later on where the top wave has moved to the right a little bit and the bottom wave has moved to the left. Now if you look closely at these waves, you can see that this corresponds here to a quarter of a time period. So in this first situation we've got t0, and here we are a quarter of a time period on. So in 1/4 of a time period here, you can see that this wave crest on this top wave has moved from this dotted line here across to the next dotted line there. It's gone a quarter of a wavelength, and at the same time, of course, this wave here, the one on the bottom, has gone a quarter of a wavelength to the left. And now, of course, what's going to happen is that the two wave crests, wave troughs, will all match up. So the negative displacements will add together at this position here, and the positive displacements will add together at this position here. We're going to have reinforcement, and what we will have now is a wave produced with a much larger amplitude than the two individual waves, the amplitudes essentially have added together. What we're going to now move on in situation 3 then is another quarter of a time period here. So this is 2 quarters or a half of a time period on from this original situation. So from situation 2 we've again moved, each wave has moved a quarter of a wavelength, the top wave again a quarter of a wavelength to the right, bottom a quarter of a wavelength to the left. And this will bring us into destructive interference again, where we have positive and negative displacements adding together. The waves will completely cancel out. Move across here to now 3 quarters of a time period. So again, we've moved another quarter of a period on from situation 3. Again, each wave will have moved 1 quarter of a wavelength on from where it was before. Let's look at where the waves are now. We've got a wave crest here, this top one, a positive displacement here at this point here, and also a positive displacement on the other wave. So the positives add together, the negatives will add together at this point here. And again, we will have constructive interference. We've got reinforcement, we've got a larger amplitude produced. And if we go to situation 5 here, now we've moved on 1 whole period. So each wave has moved a full wavelength from its original position. Top wave to the right, bottom wave to the left. And again, we've got positive and negative displacements matching up. So we will have cancellation. Now then, what is the significance of that? Well, the significance of it is that we're actually going to produce what we call a stationary wave, or sometimes a standing wave. Why is that? Well, if you look at some positions here, what you can see is that at some positions like this one, the particle at that point in the wave medium, at some points it's got a 0 displacement, and other points here it's got a maximum displacement either positively or maximum negatively. So this point here, this point in the wave medium, is actually oscillating up and down. One wave goes to the right, the other goes to the left. This particle will be oscillating up and down with a maximum amplitude. If we move on here a quarter of a wavelength, we notice actually that this particle never actually moves. Its displacement is 0 there, obviously, when the waves had cancelled out. But it's still 0 here at this point, it's still 0 at this point, it's still 0 here, and it's still 0 there. So what we've got here is some points in the wave medium which have got 0 oscillation. They're what we call a node. And at this next point here, again, a quarter of a wavelength on, again, you'll see that this particle is oscillating, maximum, or 0 amplitude there, obviously maximum negative there, 0 there, maximum positive there. So this particle here is oscillating with a maximum amplitude. This one here, again, will have 0 amplitude. It will be what we call a node. Okay, so what we've got here, some points on the wave oscillating 0 amplitude, others oscillating with a maximum amplitude, and the result of that is this stationary wave pattern. So what you arrive at is this sort of situation here then, where basically you've got nodes, what we call at this point here node, where the particles in the wave medium are not oscillating at all, and then we have these antinodes where the particles in the wave medium oscillate with a maximum amplitude here. And again here we've got another node, a node, an antinode, and a node. So one thing to appreciate with this standing wave pattern here is that the distance between one node, which if you like would be there, particle, the wave medium in that point doesn't oscillate with any amplitude, and the next node, which is there, the distance between those 2 points, between there and there on this standing wave, is actually half a wavelength of the progressive waves that actually produce them. So with a standing wave, the distance, successive nodes, is half a wavelength. So if I had produced this standing wave pattern, I could measure, for example, the distance between this node, the distance between this node. That's equivalent to 1, 2, 3, 4, 5 node to node distances. So if I measure the distance between there and there, divide it by 5, that will give the average distance between successive nodes. And then if I was to double that, I would get the wavelength, because the average distance between successive nodes is equal to a half a wavelength. So if I double the average node to node spacing in a stationary wave, I will determine the wavelength of the waves that have produced that stationary wave pattern. One other thing to perhaps consider about stationary waves at this point here is that if you notice, in a stationary wave, all particles are oscillating with different amplitudes. Okay, so you've got the particles at the antinodes are oscillating with a maximum amplitude, and the nodes oscillating with zero amplitude. That's a different situation to a progressive wave. The progressive waves that superimpose to produce this stationary wave pattern. In those progressive waves, every particle oscillates with the same amplitude. They're just slightly out of phase with each other. So if you look at this here, progressive wave, this progressive wave here, look, as it moves to the right, every particle in that progressive wave will be oscillating with the same amplitude, but they're all just slightly out of phase with each other, at least within one wavelength they're out of phase with each other. But here, when you produce your stationary wave pattern, if you're ever asked the difference between a stationary wave and a progressive wave, one key difference here is that in a progressive wave, all particles in the wave medium oscillate with the same amplitude. In the stationary wave pattern, you've got different amplitudes. You've got the maximum amplitude at the antinodes, and you've got the nodes where the amplitude of the oscillations is zero. The other thing to realise is that, of course, we've said right at the start of this topic that progressive waves transfer energy. So if you look at these two progressive waves here, the top one is transferring energy to the right, the bottom one is transferring energy to the left. But when we form the stationary wave pattern, there is no overall transfer of energy at all, and in fact energy is trapped here in these antinodal regions. So a progressive wave will transfer energy, a stationary wave will trap energy in the antinodal regions. Okay, so we've summarised there a couple of differences between progressive waves and stationary waves. One other thing we ought to mention here, of course, is that between two nodes in a stationary wave, if you think about it, the phase of the particles will be the same. Because they're oscillating all with different amplitudes, basically all these particles here will oscillate up, they'll reach the top of their displacement together, and then they will oscillate down together. So between two nodes, all of the particles in a stationary wave are moving in phase. But then they are moving in antiphase with particles on the opposite side of a node. So basically, as these particles move up, these particles on the other side of the node will move down. They will be in antiphase. Where we've seen already that in a progressive wave, the phase changes as you move through one wavelength of that progressive wave. So again, another difference there between progressive waves and stationary waves. Okay, so let's recap. What conditions do we need then to form a stationary wave? Well, really two things. So we need to have two waves of the same speed and frequency travelling in opposite directions. When those two waves superpose, interfere with each other, then we will get a stationary wave pattern produced. Now the easiest way to do that is simply to have an incident wave and a reflected wave. So stationary waves are formed from the superposition of an incident and reflected wave. So if we reflect a wave off some surface, the reflected wave will have exactly the same speed and frequency as the incident wave, but it will be travelling in the opposite direction. It will superpose with the incident wave and we will get a stationary wave pattern produced. Now one place that we see stationary waves is on a string, so let's have a look at that now. So what we have here is a vibration generator on the left, and then the string is stretched over a pulley and a mass is suspended to put the string under tension on the right. And what we can see is a wave, basically, or stationary wave pattern is set up here because the wave is reflected. The vibration generator sends a wave down the string that's reflected at the pulley, and the reflected and the incident waves superpose, and we get this standing wave pattern here. And you can see here this first standing wave pattern, we've got basically an antinode in the middle, and then we've got nodes at the two ends of the strings, basically where the string is held at the vibration generator and at the pulley. They've got to be nodes. And at this particular frequency, we have an antinode in the middle of the string. We've got one loop on the string. What we can do here is increase the frequency. If we increase the frequency of the vibration generator, that will reduce the wavelength of the wave. And if you remember, the distance between two successive nodes is always going to be half a wavelength. So as we reduce the wavelength, the distance between the nodes will decrease, and we can fit two loops on the string. And that is what we can see. As you see here, two loops in the string, node in the middle now, node at either end, and then we've got antinodes there. If we then increase the frequency of the vibration generator further, that will change the pattern again, and we can fit even more loops on the string. In our stationary wave pattern, we can actually get 3 loops on the string, and we can see that here. There we go. And again, of course, the distance between successive nodes is always half a wavelength. Now, we will talk more about waves on a string later, but that's just one example of producing a standing wave pattern from an incident wave produced, sent down the string from the vibration generator, and then reflected at the pulley. The waves incident on the pulley and the reflected wave from the pulley overlap, they superpose, and we get the standing wave pattern produced. Now, it is also very easy to demonstrate a standing wave pattern using microwaves. Now, I've linked to a video. If you look at the bottom in the description, there's a video or a link to a video of an experiment where this is actually done. Very easy to demonstrate. And basically what happens is the microwaves travel from the microwave transmitter towards the metal plate where they are reflected. And then the waves that are incident on the metal plate are superposed with the waves that are reflected. We get the regions of constructive and destructive interference. We get the nodes and antinodes produced. So if you move the probe receiver here backwards and forwards between the transmitter and the metal plate, what you will detect is a sequence of nodes and antinodes. So on the meter here that's connected to the receiver, you will get a series of maximum and minimum readings. In other words, what we will get here as we move it around, we'll get a node, we'll get an antinode, node, an antinode, node, an antinode, and so on as we move through here between the transmitter and the metal plate, which is reflecting the microwaves. One thing to appreciate is that we will only really get true nodes down close to the metal plate, because the further away a wave travels, it will lose some energy, and that means its amplitude will decrease. Near the metal plate, the incident wave here, if you like, to this first node here, will have travelled that distance. The reflected wave will have travelled this distance. So here, to form this node, the incident and reflected waves have travelled almost the same distance, which means that they will have very, very similar amplitudes, and therefore we will have almost complete cancellation at that node. If we think about one of the nodes formed much closer to the transmitter, what we're going to call a node, in this case, the incident waves, the waves from the transmitter, have travelled very little distance at all. The reflected wave has had to travel all the way to the metal plate and all the way back again. So the reflected wave has travelled far greater distance than the wave that's travelled directly from the transmitter, and so here the wave that's travelled just from the transmitter is going to have a much larger amplitude here than the reflected wave. The reflected wave will have lost a lot of energy travelling over this great distance to the metal plate and back again, so it will have a much smaller amplitude, and that means they won't completely cancel each other out. So although I've put nodes and antinodes here, really we only get sort of true nodes where you get complete cancellation down near the metal plate. You will get minima here, so you will still detect maxima and minima, but the difference between the maxima and minima will get less closer to the transmitter because we're no longer getting complete cancellation at the nodes. What we could do then, we could use this equipment here to determine the wavelength of our microwaves, because if we measure the average node to node distance, the average distance between successive nodes will have to equal half a wavelength. So if I was doing this experiment, what I would do, perhaps measure across a number of nodes here, find what that distance is. If you've measured 3 node to node distances, whatever that distance is, divide it by 3, get the average distance between nodes, and then divide that by, or times that by 2 to get the wavelength, because the distance between successive nodes is only half a wavelength. Now this experiment would work equally well with longitudinal waves. So rather than using a microwave transmitter here, we could have used a loudspeaker. We could have had sound waves. Remember, sound is a longitudinal wave. We could have reflected that off a metal plate. Sound waves reflect back. Again, we'll get a stationary wave pattern produced with nodes and antinodes, and we could just have a microphone here. So we could have had a loudspeaker and a microphone, and we could have performed the experiment with sound waves. Essentially the same result. We would get a series of nodes and antinodes resulting due to the standing wave pattern here that would be present.